Hi, I am Chung, or you can call me Edgar. Under extreme dynamics such as drifting, how do we guarantee that the agent both reaches the goal and avoids obstacles that form narrow gaps near the goal? This is a reach-avoid problem for near-danger scenarios. In this presentation, we will demonstrate a formal way to efficiently compute a backward reach-avoid set, or BLAS, where if the agents start in any of the states in this set, it is guaranteed to reach and avoid. We propose a new approach to PARC, or Piecewise Affine Reach-avoid Computation, which can compute the BLAS of piecewise affine, or PWA system with low conservativeness. Our method proceeds as follows. Given a proposed planning model defined for some state parameter bound, we convert it to a PWA system by tessellating the bound and infinitizing it using Taylor expansion. We then account for the mismatch between the PWA planner and the actual tracking performance of the agent by sampling trajectories, rolling out, and computing a tracking error bound. Online, we obtain information about the obstacles, the goal set, and the initial position. We first assume we have a goal-reaching plan that connects the initial position to the goal set in the PWA planning model, which can be easily obtained by solving a two-point binary value problem. Then, we can extract the mode sequence corresponding to the goal-reaching plan, shrink the goal set with the tracking error bound, and compute the backward reachable set, or BLS, corresponding to this mode sequence. Any plans generated from the BLS guarantees goal reaching when followed. To account for the obstacles, we similarly buffer each obstacle by the tracking error bound, compute its one-step BLS for the mode sequence, compute their convex hull, take intersection, and then backpropagate it as a subset of the BLS. The computed backward reach-avoid set, or BAS, overapproximates the set of all plans that, when followed, collide with the obstacles. Therefore, by taking the set difference between the BLS and the BAS, we can obtain the BLAS, which for all plans sampled within guarantees both goal-reaching and collision avoidance. Of course, there are many reach-avoid methods in existing literature. However, it is very challenging to compare these methods fairly because each one has a different advantage. Through a variety of experiments, we discovered a unifying challenge for all of these safety methods is near-danger planning, for which we propose our PARC method to address this gap in the literature. We believe there are three things PARC has and other methods do not, which enables it to perform near-danger goal-reaching: planner-tracker cooperation, low numerical approximation error, and time-varying uncertainty model. We show the importance of each of these with three experiments. For the first experiment, we found out that because neural CLBF has no formal safety guarantees, the agent will sometimes collide with the obstacles when the gap is narrow. On the other hand, fast track always assumes adversarial tracker behavior, so it has trouble achieving reach-avoid in these near-danger scenarios as well. In PARC, we assume the planner and the tracker is cooperative, allowing us to pass through the gap and reach the goal. Of course, there are also methods like RTD, which assumes planner-tracker coordination. However, RTD uses a different planning model and set representation than PARC that we found is more conservative. This is why RTD wasn't able to pass through the gap, while PARC could. For the third experiment, consider KDF, which uses a constant tracking error bound on the trajectory. If the gap is wide, it would have no problem directing the agent through it. However, if the gap is small, KDF will not be able to pass through it. But since PARC considers a time-variant tracking error model, it can successfully pass through the gap. Finally, because of the representation power of PWA planning model, we can also extend our method to extreme dynamics such as drift parking. We adopted drifting dynamics from existing literature and fitted a PWA model to the drifting data. In the figure, the green triangle represents the computed BLAS, the small size of which indicates that this is a very challenging problem. However, as we have shown, every trajectory generated from within this small triangle guarantees drift parking reach-avoid when followed. In conclusion, we believe PARC is a key step to providing reach-avoid guarantees on near-danger scenarios by being safe without being overly conservative. As future work, we plan to explore speeding up the algorithm as well as stress test it on more hardware examples. Thank you.